You remember when you have the two waves meeting, they make the fringe patterns, the peaks and no peaks, peaks and no peaks. So if, for example, you had some sound here, and you had some sound here, and then here's the wall, what you would get is lots of sound here, and then a little bit here, and then a little bit here. We are going to. This is -1, this here is n-1, n-2, this here is n equals -2. So, this distance here, big D, this distance here, I think we called it small d, and this distance between the peaks is s. And then this here has a wavelength, lambda. So do you remember the formula was, oh my goodness, I can't remember, it's been so long. X or lambda equals S. No, the other one. That's it. S equals lambda d, big D? Small d. Okay. Right, so here, let's say it's sound. So what's the speed for sound? It's 330. You don't need to know that. It will be given to you in the question. The frequency, let's say the frequency is 10,000. 10,000 hertz. Okay, can you calculate the lambda for me, please? Give me the lambda. Do you remember what formula you need? No, that's for the T. V equals lambda F. Yeah, so it's 3.3 centimeters. Okay, now get me the F. 1, 2, 3. We'll say the D is 3 meters, and this D will say about the same, 3 meters. Maybe 4. We'll say 4. Okay, so here 2.475. Okay, that's a little bit too small. So if I want to make this number bigger, I need to make this bigger. If I want to make this bigger, then I need to make this smaller. So if I change this to 5,000, then this would be about 5 centimeters. Let's test that. So what I'm going to do is I'm going to have a sound wave come out here. Come on. Oh dear. Not so good. Right. Pointing towards you. Pointing towards you. Right, so roughly. So I'll have two sound waves coming out of the speakers, and what will happen is the waves will come out, and part of them will add together to make a peak, and then some of them will cancel. So you have constructive if they add together, and then if a trough meets a peak, that's destructive. They cancel. Trough meets a trough, it means you have a very low trough, and if a peak meets a peak, it's a very high peak. If a peak meets a trough, they cancel. Yeah? Wait, what's that here? Peak meets a trough. cancel. Peak meets a peak, very high. And then a trough meets a trough, very low. Okay? So the right, let's have a look. Right, so for this, sit up straight, and then what? Now don't move your head yet until I tell you. Right, do I have the sound working? Not just yet. Okay. Don't move your head. Just sit straight. Don't move your head. What? Oh, come on. Okay. That's, I don't know if this is a problem with the. I should play a video to make sure it's working. Come on. Right. Okay, we won't do that one because that's a bit too loud. We'll go for something lower. Oh, yeah, that's better. Ooh, that hurt. Right, so this is 2,500, so it means that the distance between the peaks should be 10 centimeters. Okay? Let's see if that works. So don't move your head, have a listen. Then, slowly move your head to the left. And after about 10 centimeters, you should hear a change in the volume. Working?
No.
No! Hang on. Yeah. No. 10 centimeters might be too much. No, don't give me this. Notice this now?
No.
The black one is more.
Was more? Hang on. Let me stand on the back. What are you talking about? I can hear it. You're up. Yeah. One more. Now, the other problem is that the speakers aren't lined up properly, which is unfortunate.
Oh, I get it now.
don't move. Now listen to the volume. It's the same volume. It's not louder or quieter, yeah? Now if you start moving your head, it should go up and down.
Oh. This is most of this.
Can you hear it? No or yes?
Yes.
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 So right now, don't move your head. The volume is constant.
Yeah.
And then moving your head.
I found the peak.
Good for you. Great. So as I was saying, so what's happening is the two waves form peaks or they cancel. So this is, you can hear this in the change in the volume. If it was light, what would be the difference? Bright spots and darker spots. Yeah. Okay. Right, let's have a look here at our question. So, look, since nobody did this, or did anybody do this? Nobody did this, right, okay. So we'll do it together.
I should do it.
Of course. And he's not here, of course. Right, so do you remember what a diffraction grating is? Do you remember this? No.
Oh yeah.
What is this?
It's the thing where the lead.
It's the piece of plastic and has lots of slits in it. And the light goes in and spreads out. Yeah. Like this, yeah. So here we have 300,000 lines per millimeter. So that means in 1 millimeter, there's 300,000 lines. Oh, sorry, per meter. So in 1 meter, there's 300,000 lines. So my first question is, what's the distance between each slit, each line? So if you have 300,000 per meter, then how far apart are each of the slits? Yeah, 1 divided by what? 1 divided by 300,000. Yeah, so that's the first one. That's the small d. Can you calculate? Yeah. So, great. In 1 meter, there are 300,000 slits. So my question is, how much distance between each slit? 1 divided by 300,000. Yeah? So the first question, 1a, you have your diffraction grating, and there's 300,000 per meter, so the distance is 1 over 300,000. So what did you get there? 0.0000. Yes. 3.33 micrometers. Okay, so that was part A. So part B now. So what happens is you have some light and you shine it through this diffraction grating, and then it spreads out, as you know. So my question is, what is the angle here for the n equals 2 spot? And I also tell you the wavelength is 633 nanometers. So what formula do you need for this one? This is the one where you need n lambda equals d sine theta. And the d you know. The distance between the slits you know. It's right here. So you know the d, you know the lambda, you know the n. So get me the theta, please. 3.33 micro. You told me what the D was, though. Why are you asking me? You told me.
2 weeks ago.
Oh, good, yes.
Six. 10 to the minus 9.
6. Nano is 9, right? Minus 9.
-9 for nano, yeah. Did you get the theta?
No.
Oh my goodness.
No.
I have the theta. Does anyone else have it yet?
Not yet.
Ah,
Yes. 22.34.
correct. That's the theta. What's wrong? Did you not get this? Why not? What happened? So you have
I forget.
2 times 633 times 10 to the minus 9 divided by d. So divided by 3.33
Oh.
times 10 to the minus 6 equals sine theta. So theta equals 22.34.
Oh.
Oh, indeed. Yes? Right, 3. C, I mean. What is the biggest order? So my next question is, what is the biggest order, the biggest n here? Should you remember the trick here? What's the theta at the biggest?
180.
No. What's
90.
the 90? So here for part C you have n, which you don't know, lambda, which you do know, equals d, which you do know, and sine theta, which is nearly 90. So tell me what that biggest n can be. Did you get it?
5 probably.
Yeah, so what do you choose for n? N is 5.
5.
Yeah?
No.
N can only be 1, 2, 3. 0, 1, 2, 3.
Alright.
Yeah. Yeah?
5
Yeah,
probably.
5. Yeah? Yes? Okay. Now, in this next one, the red light is replaced by blue light, a different wavelength.
Oh.
And it is found that the diffraction angle for some order of red light coincides with exactly the diffraction angle for the blue light in the next order. What is that order? Okay, so this is a bit complicated. I'll explain it in the picture. So what's happened, you have red light. Red light comes in, and on the screen, you get red like here, here, here. This is 0, 1, 2. -1, -2. Yes? Then I replace the red light with blue light. So the blue light will be a little bit different. Let me think what will happen. Red. Oh, can't remember if it's going to be bigger or smaller.
Smaller.
No, don't, you're confusing me. I can't think right now. Red, orange, yellow. Red is the one. Okay. I think what will happen is the blue, you'll still get 0 here, but maybe it's not as spread out. So maybe the 1s are here, and then maybe the 2 for the blue is where the 1 for the red is. That's what I mean here when I say that the red light coincides with the blue light in the next order. So for example, if the blue meets the red at order 1, then the blue will be order 2. Or maybe they don't, maybe they meet up here. So if the blue was here, then it'll be, if it meets here, I'm saying it'll be in the next order. So, just to be clear, maybe the blue is here for 1, and then maybe the next one here is 2, and then maybe the next one here is 3. But there's some place where both meet. And the only thing I tell you about this is that the blue will be +1 on the red. So if the red order, let's say here is 0, and here is red 1, and here is red 2, and if the blue is also here at red 2, I'm saying this will be blue 3. That wherever the blue and the red meet, the blue is in the next order to the red. So my hint is to say that X is for the red, and X + 1 is for the blue, and they both are at the same place. So if they're both at the same place, what do you know about their angle? The same angle. Yeah. So anyways, you might want to write that down. There's a lot of ugly English in that, okay? So the red light is replaced by a blue light, and it's found that the diffraction angle for some order of the red light coincides exactly with the diffraction angle for the blue light in the next order. What is this order for the blue light? And my hint is to use X and X + 1 for the orders. So you probably want to write that down, all that English. I know, it's a lot. You understand here that you have the red light. So this is 0, 1, 2. And then it's replaced with blue light. And the blue light will be different. But somewhere the blue and the red will be the same. So what I'm saying is, for example, if the blue is here and the red is here, the red is 2, and I'm saying the blue will be 3. That this will be the third circle for the blue. That's what I mean here with the X and the X + 1. Yeah? Yeah. So, yeah. So here, the zeros are the same. The 1 for the blue is different to the 1 for the red. But the 1 for the red is the same as the 2 for the blue. So here they're the same. And the blue is 1 bigger than the red. This is 1 and this is 2. So this is the special place where they meet. And the blue is 1 bigger than the red. Yeah?
The same in here and here and here?
Yeah, and the minus as well. Okay. Can I do it? No? Okay, can I do it now? Is that yes? Okay, great. Right, let's have a look at this. So you know for the red, that's blue, for the red, n lambda equals d sine theta. And you know for the blue, n lambda equals d sine theta. Now there's some things you know that are the same. What's the same here? The d is the same, isn't it? And also where they meet, what's the same? For the red and for the blue, where they meet here. What else is the same? Well, the theta is the same, isn't it? So the theta and the d are both the same. So that means I'll write or and b here. So that means the n for the red and the wavelength for the red equals the n for the blue and the wavelength for the blue. But you also know that the blue is equal to the red plus 1. That it's the next order. So that if I call that x lambda red, this should equal x plus 1 lambda b. Okay, and what was my wavelength for the red? It was 633, was it? Is that right?
Yeah, 63 nanon.
And then what was it for the blue?
Uh,
506.4 nanometers.
wait, why is it 6?
Doesn't it
Oh,
blue?
15. Sorry.
Yeah, so the nanometers cancel, and I get 633x equals 506.4x plus 506.4. So then x equals x equals 4. So that means x plus 1 equals 5. So when the n is 4 for the red, that's at the same place as n is 5 for the blue. Go back up here to my picture. Yeah. I only drew 2 as an example because I didn't know what the answer was, but the answer actually is when the n is 4, that's actually the same place as the blue 5. Okay. Next part.
Hold on. Go back to.
Uh, here. Continue. Okay, so I think everybody can do the next part for me. In part E, look, part E, I want the angle for the second order blue light. So it's like the second order red light. I want the angle for the second order blue light.
So it's called the angle, right? Yeah.
I want the angle.
Minus 2 or
No, it should be minus 9. Did I write minus 7?
9.
Oh, don't believe him.
But B is
Minus
minus
6.
is minus.
That's micro, minus 6.
Micro.
Nano, minus 9.
Ah, that's why.
That's maybe why. Okay. Did you get the angle?
Minus 9?
For nanos? Angle? No, what do you mean no? It's the same as part B. Except it's just, look, part B here. The only difference is the wavelength is 506.4. But the n is still 2 and the d is the same. I want the theta. Yes. Oh, come on. I want the angle.
Is it 0.0
No,
whatever?
no. You know that sounds wrong, don't you? You're making the teacher sad.
Wait.
Have we got an angle? So he?
No.
No. It's the same as this part. So the n is 2, the lambda is, where is it? There. Yeah.
N is 2.
Yes, n is 2. The d is the same. D is the same here. Yeah. And I want the theta. The theta. Have we got theta yet?
Nope. This is 3.33
Yes,
plus
it's
1.
the same. Hey.
So let me see.
I have to calculate it. So it's sine inverse 2 times, what was the wavelength? 506.
6.4.
4 times 10 to the minus 9 over 3.33 times 10 to the minus 6. Right.
Wait. Oh, I know why. I just took 506.4.
I don't know what you're saying. Right, what angle did you get, Amanda?
17.
17.9 about. Yeah. Okay.
Which part is same as what?
B.
Ah.
Ah, yes. So if you look at what's happened here, when I had the red light, and the n is 2, what angle did I get? I got, what was my answer for part B?
22.3.
22.3. And then for the blue light, it's smaller. For the blue light, when n is 2, the angle is only 17.9. So my question for F if I have white light, what will happen? Do you remember what we said special about white light?
Rainbow color.
Yeah, it has all the colours in it. Okay, so think of white as red, orange, yellow, green, blue, indigo, and violet. So the red light will be here, and then the blue light, bigger angle or smaller angle? Smaller angle will be here. So what do you think about the green light? Where would that be?
In the middle.
Yeah, the green light will be somewhere in the middle. So what will happen is each of these will look like a rainbow. And if you were to look at the screen, so for example, like here this is n equals 0, here this is n equals 1, here this is n equals 1, well that's really minus 1. You'll have a little colour here, red, orange, yellow, green, blue. There'll be a little rainbow here. In the middle here, I still think this will be kind of just a, I don't really think you'll,
The white light is good.
yeah, you won't really get a rainbow here, but you'll get one here. Where should I draw the red? Left or right?
Right.
Very good. So you get little rainbows at the locations. Now also what I think will happen is those rainbows will get bigger as you move to the edge of the board. So at n equals 2, I think this will be a wider rainbow. They get pulled out. Anyways, that's part F.
What is the
The question is, what colour are the fringes? So the answer is they are a rainbow colour. Yes? Okay, and what is the fringe spacing for the red light? So the fringe spacing for the red light. So how far apart are the red fringes? So that's S, and then there's an S again. So the formula, I think this is G now, isn't it? Yeah. S equals lambda D over D. What is this? 633, wasn't it? Oh, did I not say what the D was? I should say what that is. Oh, I do. It's 1 meter from the screen, so the D is 1. And then the small d is 3.33 times 10 to the minus 6. So that would be really big. Too big, maybe. There we go. 0.19 meters, so that's 19 centimeters. So the last question is, how big does the screen need to be?
Very big.
Not as big as you might think, because we already know what's the biggest order for red.
19.
Now what's the biggest order for red? We worked it out earlier.
5.
5.
No, red is 4. Blue is 5.
Blue. No, 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 no. You're mixing up the question. No, no. I'm asking you part C. What is the highest order for
Oh,
red?
yeah, yeah, 5. Sorry.
What is it?
5.
5, yes. So the red at n equals 5, that's the furthest out it can be. So how many separations is that? That's 10 s. You'll have 0, 1, 2, 3, 4, 5, and 0, -1, -2, -3, -4, -5. There's 10 separations there. So you would need at least 10s, which is 1.9 meters. So if your screen is 1.9 meters, it's big enough. You can see all the pattern. Isn't it 10? 1, 0, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now I don't think this question is too difficult once you practice it. I think the difficult part is understanding it.
Mm.
But this will be a section B question in the exam on waves. Yeah.
How is it?
Huh?
Is it coming up in the exam?
There are only three things that could be on the exam: mechanics, electricity, and waves.
Is this light waves?
What do you think? Is this going to be on the exam? Remember how easy the other stuff was. What does your heart tell you? Is it going to be on the exam? What do you think?
I don't know.
Right. So what I want to do for just a couple of minutes before you go is I want to open up the mid-semester exam, and I just want you to tell me if there was some part of it that you can't remember how to do. Some of it was easy, and some of it maybe you forget how to do. So let's have a look at the mid-semester exam, okay? Because I know, Amanda, you were asking for a video, and then I decided I want to relax during my break.